So we define what a concrete state is for our first refinements, and also we compare this concrete state versus the abstract states for our initial model. And also we talk about variables, either abstract variables, only the n, or the concrete variables, which would be a, b, and c. And when we try to make transitions, since we are really trying to change the values of the variables using events as transitions, we also have to distinguish between abstract transition versus concrete transition. That's something we want to do as well. I'll give you a very explicit example in just a moment. All right, let's now go for some slides. And for both the initial model and the first refinements, both of them should be interpreted or should be executed more like an abstract state machine. It will simply evolve as the actions of the enabled events will change the value of variables. And now we have to distinguish between the context over here. Are we talking about the variables of n0, model m0, in which case that will be the abstract variable, which will be just n. And in the case of the refinement machine, the variable will be a, b, and c, which are called the concrete variables. All of them should really be subject to invariance. Again, invariance, if the invariance only involve the abstract variables, they will be called the abstract invariance. If the invariance somehow involve the concrete variables a, b, or c, they will be called the concrete invariance. In a later slide, very soon, I'm going to define explicitly what I really meant about the three notions over here. For the variables, for the states, for the transitions, for the states, for the events, and for the invariance. For these three constructs, we always have to know what we really meant by abstract versus concrete. Right? That's something I will define more explicitly a little bit later. And when we talk about events right now, we're only talking about the events that already exist in the initial M0 model. And we also got some new events, since we actually now got a notion of island versus the mainland. So we actually got different events over there. But we'll talk about the new events later. For now, we're still talking about ML out and ML in. Only these two events. So these two events are the events actually exist in both the initial model and the first refinements. Right? That's what I meant by old events. And we got so we actually got different versions for example, ML out and also ML in. You can think about the version of the ML out in the initial model. We call that the abstract version. And for the redefined or overridden, right? Remember in Java, in your Java programming, there's some kind of approximation, some analogy if you want to think about. Whenever you want to define a subclass, right? In Java, you may choose to overwrite or redefine certain methods that you inherit from your parent class. You can think about it's a little bit like this right now. The initial model is more like a parent class, and the current concrete first refinement is more like the subclass or child class, in which case we are inheriting the ML out events, and we may choose to override it or to redefine that. And let's talk about ML out first, and then we'll talk about ML in, and we'll do some exercise for each one of them. Let's say for the ML out, I simply leave the guard over here unspecified, but for now, let's only consider the action over here. So A will become A plus 1. So why is that? So let's think about exactly why the update should be the case. So in the case of the ML out, right? Over here, why is the updates A becomes A plus 1? If you think about the traffic flow, when I say ML out, I'm really talking about the cars actually leaving the island over here, right? So that's really this particular traffic over here. So that means I'm having more cars going for this particular direction. So that's why A will actually become A plus 1, right? So if you look at the diagram, you will see why. Okay, and let's now go back to this particular event over here. So that's the redefined version or the refined version. Now we want to see under what circumstances should this event be enabled to really occur. Right, so this is the meaning for ML out. It's really similar meaning. However, it's now a little bit more elaborate, right? Before we said ML out really means to really go out of the mainland and go into the island bridge compound. So this is our definition in the initial model. But right now, since we got a distinction between the island and the bridge, so when we say ML out, we really meant ML out is really about leaving the mainland and go onto the bridge. That's really what we're talking about. We're not even talking about the island, which will be taken care of by the variable b. Right? And what about the enableness condition for ML out, the guard? Let me give you some hints. Let's think about naturally. Under what circumstances should the ML out be enabled? When should cars be allowed to really leave the mainland and actually go onto the bridge? What should be the circumstances? Well, think about naturally, right? In order for the car to really move onto the bridge, you better make sure there is no other car coming from the other direction, right? So that means this part over here should be 0, obviously, right? What else? Well, let's say the car is really allowed to go onto the bridge. In that case, you should really make sure the summation of A, B, and C are still actually limited by the maximum capacity, which is the constant D that we already declared in the initial model. Remember, we got this invariant over here, right? Remember, we got A plus B plus C should be equal to N. So that means right now, in order for us to really go on to the bridge over here, we want to make sure before we can do that, given that A plus B plus C is equal to N, and also we know that from the initial model, N is actually less than or equal to D. Right? Remember, initially N is also less than or equal to D. And what we want to really make sure is somehow these two equations will actually hold. Right? So that will be my hints to you. Right? If you go back to the slides, so these are the two hints for filling out the guards for the ML out. Right? So you want to make sure only the current traffic really can only flow to the island, but not the other way around. And also the number of cars on the bridge and the island should be limited. Right? What should this guard over be? You can now pause the video and think about it. Alright, assuming that you thought about it, right? Let's now talk about one by one. Okay, so there will be two guards over here. So guard number 1. Okay, I'm just putting a label just for you to actually easily see the correspondence to the slides. But in the actual model, you don't need a label. Guard number 1. We want to make sure only traffic is really flowing this way. So that means this way over here should be 0. So that means C is simply equal to 0. That's really the first one, right? What about number 2? Number 2, we somehow want to make sure the total number of cars over here should be consistent with what we defined in the initial model, meaning that N is less than or equal to D, right? That's something we defined earlier in the initial model. You can check the invariance over there, right? So let me just give you some intermediate kind of equation to really work out a final answer. So what we have is, we know that A plus B plus C is equal to N. And over here we talk about the traffic from island to the mainland should be 0. C is equal to 0, right? And also we want to make sure they are upper bounded. So that means N should be equal to, less than or equal to D. So these are the 3 equations that are relevant for me to work out exactly what the second guard should be, right? So now, can you actually infer from here? Let's try. Okay. So you can see C is simply equal to 0. So now we can cancel this out, right? C is no longer relevant over here in the equation. And also N over here is less than or equal to D, right? And also we know that A plus B is not equal to N. So that means if you actually try to combine these two together, it should not be too surprising to come up with the conclusion over here, right? We know that A plus B is equal to N. N itself is less than or equal to D. So that means A plus B should be less than or equal to D, right? So that will be the second guard. A plus B should be less than or equal to D, right? Hopefully you see the logic of coming up with the guards over here. Let's now go back to the second events. Well, this event MLN also already existed in the initial model, so we are now overriding it while we are refining it. Let's now take a look. And for the MLN, so that means we are trying to denote a car leaving leaving the bridge and going into the island, right? Going into the mainland. So that's why mainland in over here, right? So what we are really talking about is we're talking about some car that actually go from the bridge and then into the island. Into the mainland over here, right? So just make sure this is mainland over here. And what should be the guard? So cars enters the mainland and getting off the bridge. And here are some hints for you. The MLN should only be enabled, well, thinking this way. If I'm trying to leave the bridge into the mainland, should this particular constraint be relevant? Well, actually it shouldn't be, because this one is really constraining about the upper bounds for the number of cars that can be on the bridge or on the island, which will be the summation of A, B, and C. But since now we are trying to move from the bridge into the mainland, in that case we're only decrementing C over here, right? So you can see exactly that's why we're having this particular updates over here. So that's why we are decrementing the variable over here. What C becomes C minus 1. And what kind of we know that this so in here the n less than or equal to d over here is not relevant. So we don't, since we are decrementing the value, so we don't have to worry about violating the upper bound constraint. Not relevant for this particular event. The only thing we have to worry about is if we want to really go from here to here, there should be at least one car that's on the bridge. Otherwise, how can you actually go into the mainland, right? So that means C should be larger than 0. Right? So that will be the answer. So the only guard that we have to put over here, I'll just say put guard number 1. C is larger than 0. You might be wondering, should you also put A is equal to 0? That's a very good thought. However, I would claim that logically it's not necessary, because if I say C is strictly larger than 0, which makes sense because I want to make sure there's at least one car on the bridge getting off to the mainland. And if you compare C larger than 0 and also invariant number 5, it will imply that A should not be equal to 0. Right? Let me just give you a little bit aside over here. So G1 over here, unnecessary. To also say A equals 0. It will be unnecessary. And why is that unnecessary? Because somehow the invariance together with this guard can really entail A is equal to 0. Let's take A is equal to 0. Let's take a look. So here we got invariance 1 and 5. We got A is equal to 0 or C is equal to 0. And our guard number 1 for this MLN over here is actually C larger than 0. And we know that C larger than 0 is actually going to make this particular part false. In order for the entire disjunction to still be true, the only option we got left would be A is equal to 0. Right? So that means if you actually got, let me just write it down. So this part over here will actually entail A is equal to 0. Entail implies A is equal to 0. So that's why you don't really need to put in this particular A equal to 0. Logically, it's just not necessary. Right? Hopefully you also know this point as well. Right, let's now go back. And that's about the guards for these two events. So I decided not to really present them to you directly, so we can really think about the process of deriving them. I think that's even more important than seeing them right away and take them for granted. There is one thing I would like to fix, which is about the derivation of guard number 2 for ML out. And remember, when I spoke about the derivation of this particular guard, I mentioned the relevant equations over here from the abstract states and also from the concrete model. However, there's some minor detail which I didn't really put right, which is critical. So I would like to fix it. Just bear with me. So what I would do is I'm going to wipe out what I actually wrote earlier, and I'm going to write it properly this time to be correct completely. Okay. Let me now just make some space over here so I can write it right beside G2. All right. So G2 over here. Right. So the final answer that we should really get should not be less than or equal to D. It should be instead strictly less than D. But now let me show you how to derive it. Right. As said before, we should really consider two relevant inequalities. One would be from the abstract states, N should be upper bounded by D. And also, in the concrete states, A plus B plus C should be equal to N. However, I did not actually consider, I overlooked the consideration that A is actually going to become A plus 1 after ML out was enabled and also executed, right? So that's something I didn't really pay attention to. So that's why my result was actually less than or equal to rather than less than, right? That's some mistake you definitely want to avoid, not like me. So the idea would be we want to make sure these two invariant conditions over here from the abstract states and from the concrete states, upon the occurrence of the enable ML out was taken, in which case its action will take effects. In which case A will become A plus 1. We want to make sure after such change to A, these two invariants will still hold in the post states. That's what we are really concerned about. Let me write it down over here. So what we are really concerned about is the post states over here. So let's put all the relevant invariants and also constraint over here. So that would be number 1, M prime less than or equal to D, right? We don't really prime the constant D because the constant values stay the same between the pre and post states. Number 2, A prime plus B prime plus C prime is equal to M prime, right? You can see all the variables should be prime to denote their values in the post states. We want to make sure these two invariants will still hold in the post states. And this G1 that we derived earlier will also be useful. Let me put it down over here. And of course, the guard will be evaluated in the pre-state. So that's why C is not really prime over here. C is equal to 0. Right? So these are the relevant constraints for us to really derive the G2 over here. Right? But let's see exactly how. So what I will do is I need to talk a little bit ahead of the schedule. I'm supposed to talk about before after predicates in the next video, but let's talk about it very quickly. Right? We learned about before after predicate before. So if you think about for this particular action, A becomes A plus 1. Obviously, the before after predicate should be A prime is equal to A plus 1. Right? A prime is equal to A plus 1. What about other variables? Since the ML out is the refined version, it should read in the case so it can modify either A or B or C, any of the concrete variables, but I only chose to really modify A, meaning that any variables that are not really mentioned in the action, they should stay the same value. That means it's going to be and B prime is equal to B, and also C prime is equal to C, right? So that's the before after predicate. A prime is equal to A plus 1, B prime is equal to B, and also C prime is equal to C, right? So these are the three things. Let's now do some very quick substitution, right? So what we have is A prime over here is actually going to be A plus 1. A plus 1 over here, and plus B prime is equal to B, so still B here, and C prime is equal to C. And you can see C is also equal to 0, according to the guard, right? So plus 0 is actually is equal to M prime. What's really M prime? Well, if you you actually need to recall what we said before about the before after predicate for ML out, right? Let me just write it down first, and then we can refer to it quickly. So ML out, we also got the abstract version. In that case, in the abstract version, we got the before after predicate, which will be M prime is equal to M plus 1, right? Let's verify that very quickly, although it's a bit of a while ago. Let's now take a look very quickly. Right, you can see that over here. You can see ML out in the initial model, the abstract version, the before after predicate should be M prime is equal to M plus 1, right? Okay, let me now go back to where we were over here. So that's M plus 1 over here. So M prime over here can be replaced by M plus 1 is equal to N plus 1. Okay, and also M prime over here is also M plus 1. So we got M plus 1 less than or equal to D over here, right? And let's now do a little bit of rewriting over here. If I say M plus 1 is less than or equal to D, so by some very basic arithmetic over here, so this is equivalent to say N should be strictly less than D. For example, 2 is strictly less than 3. 2 plus 1, which is 3, is less than or equal to 3, right? That's something you can think about. So from here to here, they're completely equivalent, just based on some basic arithmetic property, right? So this is one thing I can have. And let's now try to look at this equation over here. And you can see the plus 1 over here, and also the plus 1 over here can be canceled out. So what we got is a plus b. What we got, let me just put it over here, just with a little bit more space, right? That'll be the final intermediate calculation. We got a plus b is equal to n, right? So a plus b is equal to n. And we know that n is strictly less than d, which is strictly less than d. So all we need to take would be a plus b should be strictly less than d. So that's really the G2 that we will get eventually, right? So I really want to make sure this is done properly, otherwise you will just get confused, right? Let me say it again. What I said earlier in the current video was I derived the guard of G2 to be less than or equal to d. That one was wrong, because that one did not really take into consideration of the a plus 1 as part of the before after predicate over here. So that's why I try to redo it following these steps. I hope that's clear and also complete for you. All right, so the guard number 2 for MLL should be a plus 1 strictly less than d. And you should really know about the derivation process as well. That involve many different bits and pieces being put together. Alrighty. And so that's about the concrete guards I would like to talk about for the MLL and MLN.